Hello and welcome to lecture 15. We're doing yet another design case study. So these are fun, right? We could take this process of having a dream for what we want to build, identifying a simple small version of it, and incrementally extending it. Earlier this week, you saw me do a case study for designing a FIFO queue. In that design case study, we really emphasized on how to kind of get that first foothold by building a single entry queue, and then how we kind of incrementally build a very sophisticated queue. And you saw in the last lecture, now it's finally type parameterized. That's a fully robust, reusable, great queue. The second design case study, the emphasis is going to be on how can we use the features we just talked about, in this case, inheritance, to make a library of things that work together. And so, unlike the queue design, today's design is not going to have all of the code. There's going to be some cases where we're willing to show some of the code to kind of show the part we care about, and there'll be some functionality we're not going to have space to show. But we'll still be able to show kind of these key points and get that across. So let's, talk about it, right? We're going to kind of, once again, have a breadth of development plan. We're going to go from a crossbar, which is a really simple network component, to a parameterized network generator and kind of show that progression. And perhaps you can have a similar thing in mind for your project. Okay, so as always, get the notebook going. So we want to build an on-chip network. We're going to show this iterative development process, right? And so, as always, focus on the process over the result in these kinds of lectures. And today, the kind of goal is to how can I do this in a way that shows productive use of the inheritance functionalities. And so, as I said, design today is not going to be fully functional every time, every slide. So you can imagine trying to build a full network on chip. You could be a lot of things you might like. Maybe understandably, you want to have many messages in flight to have a lot of parallelism, a lot of throughput. Today's designs will not be able to do that, right? You're going to have really robust testing infrastructure, obviously really important. Today's designs will not have that. Maybe you want to have really clever things for flow control or multi-beat transfers, in other words, ways to kind of stream data through system. We're not going to have that. And all sorts of other concerns from network design, things like deadlock avoidance, quality of service. Yeah, we're doing a much simpler thing today and just kind of rolls the big picture, right? We're trying to build network components and make sure to kind of have the pieces we want and put them all together. Okay, so we've previously, in the prior lecture, built a crossbar. So remember, a crossbar is something that has some number of inputs, some number of outputs, and it's a way for things to go from inputs to outputs. And so there is kind of this all to all or all inputs to all outputs kind of connectivity here. So there's a lot of wires in the middle. But remember, if we have multiple inputs trying to write to the same output, there's only one output port, right? So the way we handle that is we have what's called an arbiter, right, which selects amongst the many inputs requesting there and only lets one of them actually send data, and the other ones are told, you've not been granted this, and you have to wait till they get a grant to actually send the data. So we wrote this code up before, and actually now I'm going to show this code again, but we've already revised using functional programming. So starting off, what are we going to need? Well, we're going to need a message type to kind of have because they go across the network. So the message isn't just the payload size; it also needs to know how many endpoints there are, so that way it knows how big the address field is. Sure. And of course, we have the I/O for our crossbar, which takes in number of inputs and number of outputs and the payload size, and then given that, it figures out all the stuff for us, right? It has all this, I/O, which of course is going to be vectors of these ports. Cool. So we have the I/O set up. And now here is the crossbar from before, but we've already actually made it more concise using functional programming. And here you can see me kind of blending both the functional programming concepts and for loops in the same time. And it's kind of a way to make it, in my opinion, least complicated, right? So let's look at what we have here, right? So our crossbar, we're going to have one arbiter per output port. So for number of outputs, we're going to have to seek, instantiating the arbiter. This is, the round robin arbiter, but that's not a, super important detail. Look at some of the combinations we have here going here. For example, for all of the input ports, we're using a for loop because we actually want to have that numerical index in order to kind of index into things. So that we're going to go grab into the input port, sure, get the ready signal, and then attach that. And look at this complicated bit of code here, but it's amazing we can do all this quickly, right? So let's kind of talk our way through it. So we're going to initialize uh, the ready signals for that thing. What's going to be based on the vec. It's going to take all the arbiters. We're going to grab all of those ready signals corresponding to it. And then we're going to uh, connect them to the address, right? Is there something missing here? Oops, there we go. Right, so let's go ahead and declare all this. Um, so there's a lot going on there, but you can see we're kind of able to kind of filter all this in. So we're declaring this, vec of all these things, right? And then we're grabbing a field out of that vec for each one of these. Um, so yeah, it's a little bit heavy, but this is actually pretty cool. We can kind of pull this off. Then so each of the output ports, for each arbiter, I'm zipping up the arbiter with the input ports. So we have the arbiter imp IO and the input IO, and then yeah, use some bulk connects. Another connection here. Here's that kind of check to make sure. Oh, this is actually for me, etc. So we've seen this before. Um, and yeah, if you want to declare this, you can say, hey, I want a new crossbar. 4 ins, 4 outs, 64-bit payload, no problem. Um, cool. So that works. But let's keep improving. So let's say, you know what? I want to use case classes. So I can use case classes for holding the parameters. So for example, I'll have a crossbar parameters case class that has the number of hosts and the payload size, and then I can pass around these params everywhere. So remember from a few slides ago, I kind of had to kind of remember this notion of, number of inputs, number of outputs, and now I just need to have this params, and that kind of encapsulates that for me. Not a huge win, but it's still something. It's kind of nice to have this there, and this shows how to kind of use that functionality. You can imagine in the real design, maybe your case class for parameters becomes really big, and the reason why I use that is you don't want to have, 10 lines of this kind of stuff. You want to just have params. So in the long run, params is a lot more scalable as your designs gets more sophisticated for holding those kind of fields, having a case class. Cool. Then actually inside the module, using the case class doesn't change things too much. We have that one case class rather than two arguments. When we need those parameters to go ahead and grab those fields, that works just fine. When we instantiate it, we not only declare we want a crossbar, we also say we want that case class to be used for the params. Not too crazy. It can all be done. Cool. Questions so far? Okay, so yeah, so we've shown, we had a crossbar. We just made it a little bit nicer by using case classes for parameters. What else can we do? Well, what if we want to use what we just covered and have a template type for the payload? We can do that too, and we can encapsulate that also into the parameters, right? So the parameters are going to take number of hosts and the payload type, and then you can see everything else kind of comes together, where the data is whatever the payload type is, reading that out of the parameters, and then we're going to go ahead and define, the ports for this crossbar. And yeah, we can have, this message going in both directions. Cool. So then, but now I want to build a crossbar, and I'll highlight one more thing we've changed. So before we had this notion of variable number of inputs, variable number of outputs. Now we're going to have the same number of ports, and each port is going to be both in and out. This is a model we're going to follow the rest of the lecture to kind of have this symmetry there. Okay, so if we go to the actual design, sure, we can go ahead and instantiate a vec, of those port IOs. Once again, using this template, um, you see that, a lot of code is not changed too much by this. The only distinction is now, of course, when I want to instantiate this, I need to say I want the case class for the parameters, and I also need to put in that type for the, the entries there. Sure, yes. This thing, that is the this is the parameter, the parameters. Um, I would refer to this as the generator I was talking about, the type generator. Yeah, good question. Cool. So our template class, yes, the code looks a touch more, syntax full with the addition of templating, but also more flexible crossbar, right? We now can take in the templated type, the parameters encapsulate a lot of stuff, and also appreciate, here I'm showing a crossbar. This actually is a lot of code you would need, and it's fits in a quarter of a slide, which is insane. If you write some Verilog, you'll be on like line 200 before you get to where we're at. It's a lot of code. Cool. So let's now go from a crossbar to a multi-hop network. And this is a very typical progression in networking, where you uh, as you increase the number of endpoints, you become more scalable. You have to kind of change your topology, right? So a crossbar is point to point for one hop, which is great, but to go bigger, you need to do something else. At some point, you have to go multi-hop, right? And so when you go multi-hop, then of course the challenge isn't just the hops, but it's also figuring out where to go each hop, right? That's called routing, right? We make a choice about how to get to your end destination along the way. And so the simplest multi-hop network is something called a ring, which is, as you can see down below, we're gonna have these routers, and each router is, in a ring, and each router also has a third port which connects to the actual host. So we're gonna do this really simple for now. We're gonna send messages around this ring. If it's at the right spot, it's going to get pulled out to that port. If it's the wrong spot, just send it forward. So the routing choices are trivial. Just, is this for me? Pull it off. If it's not for me, pass it on, and eventually it'll get to its destination. It might take n minus one hops, but it will get there, right? And this is kind of our starting point, right? Once again, starting simple and going to incrementally extend. Yes. Yes. The question is why does multi-hop become a necessity? Yeah, so if I have a 64 port crossbar the way I was building it, it's going to be a lot of wires in one place, also a lot of logic in one place. It's going to be a lot of muxes, a lot of bigger arbiters, a lot of things have a hard time scaling. And so, yeah, at some point you're going to need to go multi-hop, and maybe you have some clever engineering tricks to increase how big you can make a single hop. You can always make that a little bit more scalable, but whatever number someone says I can do that, you crank the number up higher. At some point, single hop's going to break, right? Um, so you're going to need that other capability. Cool. So then let's try to write this ring router, right? So what does it look like? Well, we have the actual ports from the prior slide, right? Input port, output port, and then the port to the host, right? And so you can see that uh, we have this port IO, which is both in and out, talk to the host. However, inside the actual network, which is not visible to the user, we're actually just sending around messages directly. We can see things. For example, coming on the input is something for me, right? Does the address match up? Um, And of course, you fill in the various fields. For example, am I ready to take something in? Well, is my output ready? Is my output valid? Well, is it for me, etc. Right? You can have these things filled in. There are some, gotchas in there kind of lurking. For example, we tell the input port we're ready for more passages. If our output port's ready, sure. Or if the message is for me and the host is ready. But for me depends on the message. So it's kind of a little bit of a loop there where our ability to take a message coming in isn't just based on how busy I am, but also what's in the payload. Because if the message is not for me, then all that matters is my output port's available. If it is for me, it matters if my local port's available. But yeah, we sketch this whole thing out. And you can see, yeah, in our output bits either get, passed through from the input or comes from the host. So this is sketching it out, right? And then the actual ring itself, what do? Well, we need from our parameters, we can know how many ports we need, right? Num hosts. Each port's going to have its own router. So we got to instantiate that many routers. And then here's more of the functional programming, magic, right? We're going to go through those routers, use a fold left pattern to kind of connect them all up so you can see, the previous and the current, and just kind of go through them all. This is the same pattern you've seen before, right? Use a semicolon and then pass on the last one, right? Previous in this case. And then for the ports, once again, take all the routers, take all the IOs, zip them up, and then, yeah, router and port and do a bolt connect. So yeah, here's a ring network that fits in one slide. It's still not quite complete. There's a few functionalities not here, but we're sure getting a lot of benefit from Chisel in this case, right? We're getting a lot of things quite concisely, functional programming, abstractions, reuse, it's all coming together. Cool. Questions? Okay, so then um, we have the crossbar. we have the ring. They're both networks, right? So what can we do to share code and make things more productive, right? And so the high level, both of them have this notion of a network with these bidirectional ports, right? From the host point of view. And so you kind of see how this comes together. Okay, we'll have this notion of a network parameter. A network just takes the number of hosts and a template for the payload, sure. The message, yeah, okay, that checks out. The ports, we've seen that before. Here's the thing. Now we're gonna have this abstract class network, which takes in network params, and it can go ahead and fill in the ports, right? And the ports are just a back of these port IOs. So this is all now shared. And what's cool about this is I can go ahead and redo our crossbar. And notice how I extend network, right? So it's a instance, it's a subclass of network. And you don't see the IO declared here anymore because IO is coming from that parent class. The crossbar body is basically the same otherwise. When it comes time to instantiate it, the fact this is a subclass isn't really that apparent to the user, right? The user just says, hey, I want a new crossbar. It's a new crossbar. We actually happen to be getting some of our code functionality from this parent class, which makes the body of the crossbar shorter, but that's kind of hidden. So that works. Cool. We do something similar with the ring network, or the ring network can also extend. Um, so the router itself is unchanged, right? But the ring network now extends the network. So once again, you don't see the IO declared here because the IO is already comes from the parent class and it comes together. So now all of a sudden we have a tiny library, right? We have a notion of a network, and a network can either be instantiated as a ring network or a crossbar. So how are we doing? Well, we've parameterized the number of hosts, cool. Parameterized data type, cool. The ring network specifically itself, it's not ideal, right? Um, a one-dimensional ring that's unidirectional means that messages could have a long latency, right? It takes a lot of hops to get to the place where it needs to go. And it's not very interchangeable with the crossbar. I mean, yes, they both are networks, but you'll see in a second how I can make that more smooth. But before I go on, questions so far? Let's go ahead and uh, keep going. So I mentioned a second ago, the ring was unidirectional, causing the hop count to be high. If we make the ring bidirectional, I'm going to half the number of hops on average, right? That's pretty cool. Now, if you're experienced with networks, you'll recognize that making a bidirectional ring makes things a lot trickier because one nice thing about having a unidirectional ring is if something's not for you, you just always send it out. Now, not only is there a routing choice if I send it out my left or right port, there's also things like deadlocks, right? You can't have people sending at the same time. There's ways around that with things called virtual channels. But that's more complexity, right? You can see why that's not the thing you build first. You kind of build your way up to that, right? We're looking into the details of deadlock today. I'm just kind of showing high level idea. Okay, we're gonna go to bidirectional. What does it look like? Okay, going bidirectional. If you actually look inside of one of those routers, you can think of it differently. So I drew the ring router before as very specialized. Here, the ring router, one way to think about it is that the router is kind of two things. It's a crossbar and it's routing logic. You put the two things together, right? So if things come in the ports, you use the routing logic to figure where it's going, and then the routing logic internally is going to tell it which crossbar port to use internally, right? That's kind of the whole goal. So we have the crossbar, messages come in, we pull off the address field, use our routing logic, etc. Right? So let's see that, right? So now for our router, we're going to have three ports, right? Which is a little bit, peculiar. Remember, we have basically ports for either direction in the network and a port going back to the host. So I'm kind of, for now, using a a comment, but you can imagine maybe you'll use an enum to make your code cleaner in the future. But how does it all come together? Well, notice how we have inside of a router now a crossbar as promised, right? And it's not using the same network parameters for the entire network, it's using parameters for just this crossbar, which we say, oh yeah, we want three ports, we got that. And so then here we are connecting up the ports, right? Sure, we do that. But look at this, right? If we go back to where's our routing logic is here. So our routing logic is this is a Scala function which takes in the uint and returns a uint, right? In other words, given a destination address, which is in the larger network, we're going to return which crossbar port we want to go to. So we're going to make that choice, right? Uh, and you can see there's kind of multiple things going on. If the thing is for the host, i.e., the address matches myself, goes out port to you. Otherwise, I want to go to whichever port is closer. So there's some math here in this mux about whether you go left or right or going to port 0 versus port 1. But you can see, okay, that we calculate distances, and then based on whichever one is less, we select that, right? So you can see that this is really kind of a pretty intimate blending of Scala and Chisel, where this is Chisel, right? This is a mux. These are working on UNITs. This is going to be hardware and design. There's going to be a mux, there's going to be comparator, there's going to be a subtract, all that good business. But this is also a Scala function, which we're going to call inside our connections, right? We're going to have that next top logic in there to kind of tell us where things go. So if I go back 2 slides, you can see that, this next top thing is actually being used to modify the address field when it goes into the crossbar, right? In other words, this is a classic networking trip kind of encapsulation, right? Where even though from the outside the user says, oh yeah, I have a message going to host 14, inside here the router logic say, oh wait, host 14, I'm host 6. I'm going to determine it's better to go out port 1. So I'm going to put port 1 on the port here. So the crossbar is going to work in that thing and then take it off and then send the right message off to the end destination. So that's pretty cool. Of course, we can wire things up. Things like for each, that's old hat for us now. A zip for each combo here to do some wiring. And then the actual network, the actual ring, same as before, we have the fold left to kind of connect up the ring and another zip for each combo to do the bolt connects. So yeah, it was pretty cool, right? We just built a bidirectional ring. It's not perfectly complete code, right? But a lot of the key functionality has been expressed here and quite concisely in this chisel. Um, so how are we doing? Well, now we can send messages in a shorter direction. We have a crossbar used inside of the network, but can we make this easier to kind of interchange with a crossbar? We'll show that now, the inheritance. So what if we want to, use that factory pattern from before? So we have a network parameter, sure, number of hosts, payload. Notice how, given that information, it's going to compute number of hosts. But notice how we now made this an abstract class for parameters. And then we can have parameters for each of the network types, right? So for now, both the crossbar and the ring parameters, they both extend this abstract class for parameters. They have the same fields. You can imagine maybe making new network topologies that have more specialized fields. That would totally be supported, right? So you can see how a lot of things take just network parameters and it works just fine. It doesn't necessarily need to be too, complicated based on the child classes, right? The ports, the network itself takes the network parameters. That all comes together. Now, I can revise both the crossbar and the ring router to take in the corresponding parameters for each type. Sure. And then what's interesting is now, of course, I can have this factory method, right? So I can have this object network. And then given these parameters, I can say, oh, you give me a crossbar, I'll give you a crossbar. You give me a ring parameters, I'll give you a ring. Now, this code can be a little brittle at times, depending on how it's implemented, and you might get that type erasure warning I was warning you about. But for now, it's working. So, yay. Um, cool. Now, what have we done? Well, we've parameterized everything, but it's also much more gracefully interchangeable with crossbar, right? You can imagine someone in their code, they can just say, I want a network, and they can say, I want a crossbar or a ring. And it's the parameter type passed in is what actually makes that choice. And internally, of course, it does all the right things. And so you can see there's a lot of ability to kind of build up this whole world of generators using abstractions. Cool. Questions so far? So we built a crossbar, we built a ring. What about a mesh or a torus instead of just a ring, right? And we keep sharing things and using these abstractions. And of course, the answer is yes. So what abstractions we're going to be reusing? There is a notion of a router, the idea of a crossbar combined with routing logic. There's also the things we want to use to interconnect these routers, right? You saw how between like the ring and the crossbar, there's some connection work, how do we connect up the routers in that ring topology? How do we kind of make that all come together? So for those of you hear me keep hearing me say this term torus, here's a picture of a torus, right? So a torus is basically a mesh where we also have this link going around to complete it, right? So um, this is a 2D torus. If it was a mesh, it would be a 2D grid, but without these long links wrapping around. So you may recognize that a 1D torus is actually just a ring. So a ring is kind of a degenerate case of a torus. And the more general patterns, you add dimensions to kind of keep adding on these other dimensions. And you can see that, even in this case of a 2D torus, each of these routers has to have 4 ports for the network and a fifth port for the actual host, right? So you can see basically, the pattern is 2 ports per dimension, um, and then and then plus 1 port for the actual host. So from the outside, someone using your module just sees, ports 0 through n-1, but inside your, module is actually this massive network, which has a 2D torus topology for now. So let's generalize our notion of a router, right? So our router takes in some number of ports. It has the last port attached to the host. It has notion of next hop logic. As you see, we use the next hop logic whenever we instantiate it. Um, and it connects everything up for us. And now we, of course, can also make a multi-hop network, which extends our network abstraction. And our multi-hop network, of course, has a notion of routers. We're going to have a function to connect the routers. And then it's, of course, connect the routers up and then connect the routers to the outside world. So you can see how it's only these handful of these places with these abstract classes where what child class need to fill these in, they kind of give the rest of it for us. For example, to make a new router, assuming you're using the same internal topology of a switch, I really just need to describe the next hop functionality, and I get the rest of this already kind of reused. Meanwhile, on the actual network level, same thing. I need to describe how these routers are connected, and it's going to kind of do the rest for me. And that's pretty cool. It needs to take in the router type to know to grab the right, router to right routing logic, but we can do that. So look at this, right? For a ring router from before, to re-implement that same functionality, this, bidirectional ring, we just need to describe that next hop logic. And then the rest of the stuff carries over for free if I ran this code first. And in the ring network itself, we just got to describe the connection process. In this case, we're using the fold left pattern. Oh yeah, we instantiate the routers too while we're at it, by assigning them all consecutive IDs. But you can see this is actually surprisingly concise, right? This is, capturing the key essence of what this ring router is, this ring network, in a handful of lines, because a lot of the stuff that's reused is all in the prior slide, right? This notion of how we kind of wire things up inside of a router and having things kind of in conjunction working with the crossbar, as well as even the network itself. And so we built up some pretty cool abstractions and we're using them. And like I said, these abstractions aren't always obvious when you first start a project, which is why it's helpful to, write things, get them working, maybe write another instance and then kind of see the two and look what's similar, what's different, figure out a way to kind of identify these abstractions and pull it together. And this is kind of the whole essence of the Agile approach, is that some of the abstractions are really hard to see from the beginning, and it's easier to kind of see some of them along the way. Doesn't mean you can't start or shouldn't start with a plan. It just means be ready to kind of keep adapting. Cool. So then, how about that 2D torus we talked about, right? So maybe our 2D torus will have the flexibility to have a number of hosts and number of rows, so it's not required to be square, but it doesn't need to evenly divide, of course. So yeah, we might care about how many number of columns. We usually only need to tell us number of rows, number of hosts, and we'll figure out the number of columns for them. Sure. Um, and so, as you see in my aggressive comments here, this is not the full functionality, but conceptually, we just need to give it the next top logic, and we're set. And then for the network level, same thing. We need wire up the connections in 2D for that connect routers function, but we're able to reuse that same functionality, right? So this abstract class is giving us a lot of mileage, right? We're extending multi-hop network, or extending the router, and we're getting so much from it. Cool. So we did it. We built a pretty cool system. We can put this behind a factory method. So we can say, hey, give me a network. Someone gives the right kind of parameters in there, and we get the right instance returned back to us. Notice how, in this case, we have a ring network of ring parameters. We could also alternatively recognize if someone requests uh, a torus with one dimension, they should have requested a ring, right? So we could say, hey, you know what? We did that. This is kind of cool. You can do like pattern matching, right? You can recognize that case. So her array for pattern matching, you can actually say, you know what? If there's a one-dimensional torus, you probably want a ring. So the question was, okay, if I did or did not have this optimization, how different is our ring generator from our torus generator working on one dimension? The answer is it depends because we didn't actually show the body of a torus generator in this lecture. But you can imagine uh, maybe your torus generator does produce basically the same thing as the ring when it's one dimension, or maybe it does not. Maybe it is different, right? And that's possible. I include that line as a comment here to kind of show the power of pattern matching, where sometimes this occurs, right? You can imagine normally you use some sort of if else or whatever. With pattern matching, I can say, hey, give me a torus param. When there's one dimension, I want to know that case. And otherwise, let it fall into the regular torus parameters case. So that's kind of a pretty nice use of pattern matching. Um, I think it's pretty spiffy. Cool. So we saw yet another case design study today. Um, and some general lessons come from this, right? With regressive design, really the goal is to get going, right? So make something small, get something running, get it working with a test bench, get it passing the, compiling, get it, running, um, and then keep extending and optimizing it, right? And then when it comes to finding these common abstractions, it's easier to generalize when you have more than one instance. Maybe it's different parameters, or maybe it's actually a full-on different class, but those opportunities kind of become more apparent, right? And then it's kind of seeing for reuse, right? This is a common thing where when you're writing code, if you find yourself saying, oh, I need to write this code and start this code, I'm going to go copy and paste this code from some other portion of my code to start this portion off. If you find yourself copying and pasting, that's probably a sign of opportunity for reuse there, right? So maybe you should figure out a way to pull out that more general functionality, abstract it, and make it reusable. We've shown you inheritance this week in the last lecture, as well as now making this kind of library of network generators. We've also shown generics, the templating, right? And so right now you're in pretty good shape for what you can do with Chisel. So to kind of give an outline for some remaining lectures, we will be covering memories next week. So some details of memory we didn't quite cover some more depth. And then we're going to kind of change gears. And we're going to go from talking a lot about code to talking more about general design methodologies and things we aware of about physical design. Um, in the remainder of the course, we will have more design lectures as well as things involving the project, both the project proposal reviews as well as the project presentations at the very end. And we're going to have the good fortune for some guest lectures. So keep an eye out for those. Okay, well, thank you.